Jhih is currently a PhD student in NTU, Department of Mathematics. His advisor is Professor Lin Taijia 老师. Jhih's research interests are in partial differential equations and with some numerical analysis. For PD research field, semigroups are used to model the evolution of the solution. And today's topic is about the Markov semigroup, especially for finite Markov chains. The main contents will follow Jhih's paper, which we sent earlier through the email. Okay, it's about time to start the talk. Let's welcome Jhih.
Oh, thank you, Yanqi. This is titled Final Property for Markov Semigroup of Finite Markov chains. And here is our contents and introduction. The Markov chain has been used to study the change between different states. The basic theory for Markov chains usually concern a finite and fixed number of states. So the corresponding transmission matrix can be described in a finite size matrix. However, in the past several decades, the states of chains with a larger state space has been studied, and some different analytic analyses are proposed. The main goal is still to understand how the missing time grows as the size of the state space increase, where I mean missing time for the number of states required to reach some target distance to the steady state. In theoretical computer science, the usual task is to show the missing time is a polynomial in the logarithm of the state space size. Even in mathematical setting, we can study the infinite probability space, but for application, we usually consider a finite probability space. Here is our key point. And it is well known that the evolution of a Markov chain on finite state space can be characterized by a one-parameter semigroup. That is a PT. And using functional inequality to analyze the missing time is efficiently measured. In our present, the author, Abra and Mass, introduce a new notion of Ricci curvature bound for discrete space, and use the geometric flow to obtain the desired functional inequality. In this talk, we will introduce the paper which read in 2020 by Earth and Mass. Here is section 2. Firstly, we consider a finite set X. So it is a finite set. And we let an irreducible Markov kernel K. That means the summation on Y is 1 for any X belong to X. In addition, according to the Markov chain basis theory, we know there exists a unique stationary probability measure, or you may say a steady state. That means pi satisfies this condition and this condition. This condition, we may consider this as a probability, and this can be regarded as a k times pi s equal to pi, and do summation. This likely is transition matrix. Then according to for a discrete sample space, we also can consider a probability density, which can be denoted as this. So for discrete space, we can consider density function. So usually we consider continuous probability space and with density, but in discrete space, we also consider this. And in particular, the constant function 1 between this space, because by this condition, so when we put rho x always 1, then this summation becomes this. So indeed, P of x is non-empty. In addition, we also consider this stationary probability measure stated by reversible condition. That means k as y times pi x can change s and y. That is, when we replace x by y and y by x, that is equal. And this condition is good because we may notice by this, when we use reversible condition, this form can be rewrite as this, pi y k yx. And this summation is over s. So pi y is constant, and we write pi y x k yx. Or okay, and this summation we can use condition 1, and now it is 1, so equal to pi y. Okay, this is we consider Markov kernel and induce pi. And next concept is a matrix W, which can describe the distance between two probabilities. So W square, that means if we consider W is nth square root, and here we take 1/2 and the integral by this over all probability density and psi. Psi satisfy a discrete continuous equation. Here, this equation we can write as this form. Here, d over dt we can write as dot, and this term we usually can write as this form. I means this. And this equation usually arises in the bridge mechanics, and usually referred as Navier-Stokes equation. And the rho in usually means the density of the mass, and gradient psi usually means the velocity. And here we may notice that this form usually can write as this A. A means Asian, and with the rho L2 known. And here we present a letter by our discrete setting. And here rho hat we means this. This is different from classical Navier-Stokes equation because the classical Navier-Stokes equation is right this form. So here is a different. Here means rho hat, but classical is rho. And next concept is entropy. This entropy is well known defined by equation 2. Is summation pi times rho and times log rho. And by this definition, by this concept, we have the following definition. If we say macro kernel K has non-local ridge curvature bounded from below by kappa, I means if constants be geodesic rho t in this space, we have the this concept convex condition if kappa equal to 0, and if kappa non-zero, then we have this this term to correction it. And we usually you write as this. Reach curvature of k greater than or equal to kappa. That means this inequality. And we omit this term, then we may see this is a convex condition. Here, rho t, usually we may write is this, and pt means the macro semigroup, and sometimes we write is this, k minus I. Okay, and in addition,
sorry,
yes.
may I just ask a simple question first? So the quantity is continuous in T and discrete in X and Y, right? I'm just trying to make sure.
X and Y.
I mean, what do you mean discrete setting? Are you mean discrete in X, the label chi?
Label chi. Which here's I mean chi is a finite set.
Yeah.
I mean yeah.
So
I is a between 1 to for some n.
So the discrete means here.
Yeah. Or you just say X is a finite set, but I mean discrete because we use many L2 norm or gradient sum notation. For example, here usually we refer to this is a gradient per psi t. Yeah, I mean gradient phi means phi s minus phi y. By y. Here, gradient is a 2 argument as y. For example, discrete setting which present later because I don't want to introduce many notation to confuse the reader.
So till now it's not discrete setting yet. It's still continuous.
Yeah. So we emphasize this is discrete setting because this term is not likely from this because if we don't know any discrete setting. Okay.
Yeah. Okay.
I think Mingjian is right. Continuous in variable t and discrete in variables x and y.
Yeah. Here rho is 2 argument because I noticed that rho we can put here and here, but when we put for example 0, I get a function in probability density, and I put t, I can also get a probability density. That means I put rho becomes rho t and belong to here.
So the domain 0, the interval 0 to 1 is referred to variable t.
Yeah.
Okay.
Refer to t.
And
but this notation is in paper, so I don't want to change it.
So the other question is that you in this kind of a problem, Markov problem, are you basically treat the pi x as the wave function, the weight you are using in the like entropy or whatever?
Oh yeah, it is a weight, right?
Okay.
Yeah.
Thank you.
Yeah. So we usually times pi for many times because if we do inner product for per psi, pi and per psi, we usually write a subscript for pi. That means do summation and so on, and we usually times pi.
So this is usually given from the beginning and didn't change.
Yeah. So sometimes we maybe can omit this notation, but in this paper we usually write it.
Okay, thank you.
Yeah. And here is a district form. District form here we consider here, and we may refer to here, as you can see, because this term we may refer to gradient gradient per side and gradient by and gradient per side, and we times ksy pi x. So we refer to this is the inner product under pi, and this inner product is for district form is well known because we have a following note. In partial differential equation, we usually consider the Poisson equation, and sometimes we times the test function b, I times b, so we have minus b u Laplacian u and fb, and we integrate it over domain, so we have this, and this we usually refer to standard inner product in L2 space, and this we use the integration by part. So the Laplacian usually refer to this form. So this gradient divergence can move to function b. So we get gradient u dot gradient b and write it as the inner product. And this can refer to S on u b. And we can use this to study the regularity and weak solution. And final concept is visual information. Here, visual information we set is by I rho equal to E rho and log rho. And usable fact is entropy PT rho. If we do time derivative, can get minus visual information of PT rho, and PT is our Markov semigroup. With the classical notation, the visual information usually defined by this. So we may do some calculate and find gradient rho equal to rho gradient rho. So this term can become this and cancel rho, so become this. And here we notice that this can write as gradient rho dot gradient rho over rho. So can write as inner product, and this term can become this. So this definition is concise to the classical definition. But we emphasize this definition is decreased because the district form defined by here is a discrete type. So with this is concept, we can present the main result in this paper. In this paper, he introduced the functional inequality in theorem 1.5 in this paper. Here, K is irreducible and reversible macrokernel on finite set. So we have the following four inequality. The first is if we have the curvature bounded below from kappa, and then we have the HW inequality. Here, H means the entropy and W means the matrix W. And if kappa equal to 0, then we immediately can discard this term and get this. And if we have the reach kappa greater than a positive constant lambda, then we have the multiple log-Sobel inequality as this. But in here, we usually can use the one, get the HWI, then get the NLSI. we present this later. And the third inequality, if K satisfies the NLCI, then we can get multiplied telegram inequality. We write as the TWI. And if we have a TWI, oh, it's just a typo. Here is TWI, I lambda. Here lambda means this constant. And we can get a Poincare inequality. And here, this is a Dirichlet form, so we may write as this. It's gradient per side L2 known. Here L2 known means the inner product under pi. So here, this means the gradient per side dot gradient per side inner product under pi. This is a standard Poincare inequality because we can use the gradient L2 known to control the function of by L2 known of function by. And so far we have the trend of the functional inequality. We can show a ridge curvature if greater than a positive constant, then we can get HW inequality and get the multiplied log Sobel, and then get the multiplied telegram, and then get the Poincare inequality. Besides, we also can get the T1 inequality. This usually refers to transport cost inequality. And here, T1 2 lambda means this. And this inequality can be get from the proposition 2.12 in this paper. And here, W1G means the standard L1 Western matrix on PX. But this inequality is not really important, so I just point out it here. So later we will present the proof about this is functional inequality by this order. We will prove it first and this, and introduce the discrete setting to prove this, and then this. Okay.
Sorry. Before you proceed, can you remind me what's the metric lowercase the index, the index
lower index.
The W
index.
The metric the W.
Oh, here. Yeah. The G means the graph distance. Oh, you means what is the W1G, right?
Yeah.
Yeah. Okay. I write it, but I think this definition is so ugly. That is this. If WPD, P is a number, a particular number, and D means a metric. That is defined by this form. I write it. Okay.
Can I ask a question?
Yeah, of course.
So, can you briefly explain the application for this chain of functional inequalities? So, what can we do from this chain of
I know your questions. If we can get functional inequality, and then we can use this inequality to estimate the missing time, how to rapidly converge to the steady state.
Okay,
usually we can use this to estimate.
So, which inequality in this chain of functional inequalities can be used to estimate the mixing time?
Usually use
because here we have a bunch of inequalities, right? And we have the implication relation between the chain of functional inequalities. So which one? You mean we need every inequalities in this chain to obtain to estimate the missing time, or any of these can be used to estimate the mixing time? So do we use a particular inequality in this chain of functional inequalities, or we need the implication of all of the chain of inequalities?
I think it's here and here can be used because
which one?
This and I miss this because this form can be referred to. Can be referred to.
So
yeah.
So the last one.
The last one, yeah.
The last one with the older one was a certain distance, right?
Yeah.
Okay, so okay, and my second question is that so your goal is to generalize this chain of functional inequalities to the quantum case?
Yeah. This work is published in 2017 and 2020. So far I know. Yeah. So
which one?
Here,
which result has been because
as
far as I know, the last inequality, the one spatial case of the last inequality is called the Martin's inequality in the classical case, and also in 2020, the MIT group has proposed the quantum order one Watson distance. So they also obtain the Martin's inequality. So the last one has been known in the quantum case.
Yes. Yeah. You are right. So yes, this inequality has a quantum setting. Yeah.
Yes. So okay. So question is that there are something that have been known, and what's the gap you want to fill?
Oh, I think because I try to read the 2020 or 2017 the paper, but I think it's a I need to know how to get the classical sense and then to keep to reach the quantum setting. Yeah, for me. So I read this paper and present it, but I'm not ready to read really read the 2020 paper or 2017. Yeah.
Okay. So
and if you want to know, I need to say here the rich curvature to get the H1 HW inequality is to need to generalize. And but here and here can follow the step 1 and 2 can follow this paper to get the same inequality.
Okay, so first of all, I think the audience are interested in what applications of this chain of functional inequalities, either in the classical case or the quantum case. And if you are interested in the quantum case, there are some known results. For example, like you have mentioned the 2017 and 2020 papers. So but there are so many results, and there are so many known results, and there are also many unknown results. So so I think, but there are too many inequalities here. So I think the audience is it's difficult for the audience to understand which is known, which is unknown, and what is the open problems, and what is the applications of what's the importance of the unknown inequalities. Okay, let's do just my comment. So I think let's then go on.
Our goal is to improve the sum inequality on spatial case to get a better constant. For example, we know H1 HW inequality lambda can get NLSI inequality with the constant lambda. But in our conclusion, we may notice some case we can improve the constant. So this is what to do. So we need to know how to do this inequality and find a method to improve it.
Okay.
Okay. So I want to go to some proof, but some proof. Okay, the first one is HW inequality to get the modified log solver inequality, and here we recall the inequality is this, and we want to get the right hand side, it becomes this, so we can use Young's inequality. Here is the sy less than this term, and we may notice, we may set X is the matrix W between row and 1, or here 1 is the need to border, and Y is the square root spatial information. Then we have the list, and then we move this term to left hand side. So I'm minus lambda over 2 and square root. Here we need to notice that this kappa is lambda. Oh, I know I just a typo. And then this, and greater than this term. And we may notice this just this. So I can get this by a Young's inequality. And this proof can be used in quantum sense. And we just modify, because we need to find a suitable modified log solver inequality in quantum sense and HW inequality. And next, we show the modified log solver inequality to get TW inequality. And TW inequality means this. Because I have no space to put it, so I write here. For all row in the space. But it sufficient to prove this inequality holds for row in probability density plus, which means the function rule always strictly positive. Then we can use a standard approximation to show this inequality holds for all px. And then step 2. Step 2, we fix a probability density belong to P plus, and we set rho T is PT rho. And then we can use the best case macro trend theory. No, rho T goes to 1. So we have the entropy goes to 0, and the matrix goes to this by the continuity of the entropy and W. By step 1 and 2, we have the 3 and 4. Step 3 is the main trick. They also define a function f, positive from positive, by this non-negative. Ft is W rho T and square root 2 over lambda entropy rho of T. And it's clear put T is 0, we have the less term. And we know rho 0 is P0, rho la is rho. And when T goes to infinity, and this term goes to 0, and this term goes to the matrix W between rho and 1. And we notice this term and this term is multiplied telegram inequality, right hand side and left hand side. So we just need to show f is non-increasing function. And so we can compute the upper right derivative of f, because we don't know f is a differentiable function, but we always can compute the upper right derivative. And here the upper right derivative we define here. Upper means the limit sup, and right means the h goes to 0 from right. And we can compute by some simple computation to get w w derivative can be upper bound by square root I, and the last term can use the derivative entropy pt rho equal minus pt rho. So we have a list form, and we may use the multiply log sovereign inequality to get here. That means I means we can rewrite this inequality as this form. It is less than this, and we can get this. Okay, and here for rho t always non-equal to 1. But if rho t for some t equal to 1, then rho r always equal to 1 for any r greater than t. So we also can get the multiply telegram inequality. Okay. So far we don't need to use the discrete stated to prove this and this. But we want to get the rich curvature bounded below from kappa to get the HW inequality. We need to this. So basically, we define a discrete gradient and discrete divergence by this and this. The gradient means the difference, and divergence means this. So here we times k. But when we do inner product, we need to times pi, state pi. And we also have the Laplacian. Laplacian means this. So we know the Markov Semigroup usually has this form. But in this case, we write this form. This is a continuous case, and this is a discrete case. And here in the product, we set for this case and this case. This is for scalar function, and this for two argument function. So we have this, and the other we have inner product and have the integration by plus formula. So this gradient we can replace to the other argument to psi and get a minus. And L2 known means inner product under pi. And but this proof in section 2 to section 4 in this paper. So I just sketch how to prove it. The first step we need to establish the property of the matrix W. And this paper do equivalent definition in section 2.2. That means in here W squared equal to the L2 known rho 2. T equal to the something infinite. The paper say A prime, but however, you change the definition to another and use it to do some estimate. And besides, usually we use W square not to W. So when we see W square, then we have the convexity. And besides, we have the lower bound and upper bound in proposition 2.12 and 14. And when we have the property of the matrix W, then we can do rich curvature kappa. And here we omit the section 3 because he usually do some prepare for section 4. And the key point is to get the equilibrium definition of Jhih curvature has a low bound of kappa. T equivalent to this. This is a evolution variational inequality, and this inequality means this. And later we use this inequality to get HW inequality. And here the first step is use nu equal to 1 and t equal to 0 in evolution variational inequality. And we say here, when we put here is the 1 and t is 0, then we have this rho and 1, and here kappa, and here is rho and 1. And here we have a 1, and here is the rho. So we may remove this term to left hand side and remove this term to left hand side, right hand side. So we have this form, and put t equal to 0. So the derivative we also put t equal to 0. Okay, and entropy 1 is 0, so we omit this term. And so we step 2 need to estimate this term. And by definition, the upper right derivative, we may write this form. Here we notice this minus, so limit sup be changed to limit inf. And here we use the triangle inequality to get this form. And this term, take limit sup can be 0, and this term can use the proposition 71 to get this. And so far we put this term to this, get the HW inequality, the proof. And next, we show TW inequality can get the Poincare inequality. And here we need to use the discrete setting. That means I know this again we need to modify the probability density, because the rho may be for some x equal to 0. So we multiply by here. We set rho epsilon equal to 1 plus epsilon rho, and always positive. And we can notice when epsilon goes to 0, we have the approximation epsilon square 1 over epsilon square times entropy goes to this. And similarly, the visual information can go to this by some direct computation. And step 2, this is the inner product phi to phi, and we can use the continuous equation to write as this form, and then use Holden inequality and can change to this. Then less than this guy. Then here we can use the multiply telegram inequality to get becomes to this. And by step 1, we know this form can goes to this, and this term goes to this. And we can cancel this term it. So we have the rho pi less than 1 over lambda square root gradient pi. And we can do square and get the Poincare inequality, and the proof is n. And here is our conclusion. In this talk, we show the Barring trend of functional inequality by here, but we omit this on finite Markov trend. And we want to express this result can be extended to quantum setting. We may see 2020 or 2017 by Mars. And we may see this trend can be multiplied by this barring. And here T1 2 lambda means this TC1 C1. And similarly, we have the TC2 C2. TC1 C2 means this. This means the power P transport cost. And in this paper, we also notice we can use transport cost inequality and HW inequality to get the multiply log solver inequality by this parameter alpha. So here we find many problems to do because we can use some inequality to improve the base constant and get a better estimate for missing time. And the third is our future reading. We may read this paper because it is under based on quantum setting Markov semigroup. So maybe some interest reader can see this paper. And this is our conclusion. Thank you.
Thank you for your talk. Does anyone has some questions about this talk?
May I ask the Ricci curvature? Do you have some kind of curvature here, or because you are in the discrete setting, then where does the Ricci curvature comes?
You means Ricci curvature how to set under discrete setting, right?
Yes, and is there any meaning of the curvature?
This is a good question, but I think this problem for a long time. But this paper and the other papers seems not give a insight to how to define this curvature by this. I'm not sure how can relate this inequality to this because I don't really know.
And do you have any hint from their inherent metric, like D or something? Do you have any definition of unmetric D, which will lead to the definition of Ricci curvature? Is there any?
You mean this any D?
I mean, Ricci curvature should be defined from some more fundamental metric D, I suppose. So is there any definition and any kind of setting people are interested?
Are you finding the rich metric tensor something?
Yeah,
like
I'm
that?
saying metric tensor.
This is not defined by the metric tensor because the definition in this page is the lower bound of the Ricci curvature. It's a higher level of abstraction of this concept. This inequality is the definition of Ricci curvature is bounded below, but maybe the Ricci curvature itself is not defined here.
Yeah. We now say Ricci curvature is what? What is Ricci curvature? We don't say, but we say Ricci curvature bounded below by kappa means this inequality. So what is Ricci curvature K? No, we don't know.
Okay, you can think a concept like intuitively think of if the space is curved sincerely, it's curved very curved, so the entropy will lose very fast, and this inequality captures the losing rate of the entropy. So something like the curvature is very bounded below means it is very large. So the entropy will lose in a rate faster. So this inequality links to two things. One is the entropy and one is the curvature, but no definition of the curvature itself.
Yeah,
Okay.
because if you see the textbook from differential geometry, we may see a rich curvature usually defined by this bond, which is two argument, x and y, and usually defined by this bond. But I think this is not a generalization from this, so I don't present this. Yeah. So so far I don't know the rich curvature be here. What does it mean?
So if you are interested in the definition in more detail, you can refer to the famous book called Optimal Transport, Old and New. It is written by Villani. So the detailed definition of this curvature can be found in that book.
Yeah.
Okay, thank you. Yeah, maybe later you can just write them down so people may find it if people are interested. And I have another question related to Haotong's question, I think. So from the application side or from the practical point of view, because you define many inequalities, so which inequality, like inequality in rich curvature or in entropy or in psi or f, which one is more related to the object people are interested? I mean, what?
I think it's Gauss and differential because we can get the missing time can be estimated by differential rate or differential minus t square. Yeah, Gauss means this and differential means this, and we can get the best constant k in here. So when k is larger than goes to 0 or goes to steady state, means rapidly. Yeah.
Oh, okay,
Yeah.
so can you show do you write down the full formula previously? Can I look?
Yes, but I can write for us in here. Here I means differential means this bond, but this bond is a classical setting, not quantum setting. Okay, I write it by this. I means this take a differential to get. I refer this inequality to the paper proposition 7.7. It has this term and differential t rho. Yeah. This means sum the just expression value over pi. So we have this estimate when t goes to infinity and this goes to 0. Sorry, this is not differential. This is Gaussian. Yeah. I mean Gaussian. So here we estimate by lambda and here 2 lambda and here we get 2 lambda by here. So when have a more larger lambda and the rate is more rapidly.
So thank you. So in the quantum setting, so does people use are people using the quantity psi as the quantum state? So they are estimating. Okay.
Yeah.
Okay, thank you.
Are there any questions about this talk? So this this talk is I'm co-work with this Lü Zhihong. So this is a starting talk. So maybe we will introduce the quantum settings based on this trend of inequalities in the future lectures or future talks. because we are all from classical mathematical field. So when this talk is a starting point or a link to raise the interest for the mathematical friends in NTU or somewhere. So we can start from this point to extend these results and survey some quantum versions in the future. So this is serve as a starting point of this series of talks. Are there any questions about this? If not, we can end of this talk and let's thank the speaker again.
Thank you.
Thank you.
If someone have interest in about this topic,